Henrik Mellon was staring at a spectrum he had waited 3 years to see, and for a moment he did not trust his own eyes. It was June of 2023, and the astronomer, then at the University of Leicester, had just pulled fresh data from the James Webb Space Telescope, pointed at a planet that had kept one particular secret longer than any other world in our solar system. He was looking for a single, faint, spectral line, a signature so specific that only one thing could possibly produce it. And there it was, sharp, unmistakable, glowing brighter and clearer than he had dared to expect. Mellon later admitted the moment genuinely shocked him, not just because they had finally found what they were looking for, but because of how obvious, how vivid, how undeniable it turned out to be once Webb actually looked in the right way. What Mellon had just confirmed was something astronomers had been hunting for since 1989, direct proof of auroras glowing in Neptune's atmosphere. But that discovery was only the beginning of the story. Buried in that same data were two more surprises, and together they would reveal that the last, most distant giant planet in our solar system had been quietly transforming for over 3 decades, while nobody on Earth had any way of knowing it was happening. Let's go back to where this mystery actually began, because the setup matters as much as the payoff. Neptune sits nearly 3 billion miles from the Sun, so far out that it receives roughly 900 times less sunlight than Earth does. In the entire history of spaceflight, only one mission has ever visited it up close. Voyager 2 made its single flyby on August 25, 1989, screaming past the planet at a distance of less than 5,000 kilometers, gathering in a matter of hours nearly everything humanity would know about this world for the next several decades. Among the data Voyager 2 sent home was something tantalizing but frustratingly incomplete. Faint ultraviolet emissions that looked like they might be evidence of an aurora, the same glowing atmospheric light show that produces the northern and southern lights on Earth. Auroras had already been confirmed on Jupiter and Saturn by that point, and would later be confirmed on Uranus as well. Every other giant planet in our solar system had this phenomenon nailed down. Neptune alone kept slipping away from confirmation, its signal too faint, too messy, too inconclusive to actually prove. For the next 34 years, this became one of planetary science's quiet or unsolved puzzles. Astronomers using the best ground-based telescopes available kept aiming. Instruments at Neptune's poles hunting for a molecule called the trihydrogen cation, written scientifically as H3+, the reliable chemical fingerprint that had confirmed auroras on every other giant planet. On Neptune, it simply never showed up. Search after search came back empty, year after year, until Neptune earned an odd, almost embarrassing distinction, the only giant planet in our solar system where scientists could not confirm a phenomenon they were almost certain had to be there. Which brings us back to Mellon's spectrum, and the moment everything changed. Using Webb's near-infrared spectrograph, an instrument built with a level of sensitivity, Voyager's scientists in 1989 could not have imagined Mellon's team finally caught it. An extremely prominent H3+ emission line, unmistakable, glowing exactly where auroral activity would produce it. After 34 years of searching, Neptune's hidden light had finally been caught on camera, so to speak, published later in the journal Nature Astronomy with Mellon as lead author. That alone would have been a satisfying, headline-worthy result. But this is where the story actually gets interesting, because confirming the aurora existed turned out to be only the first of 3 surprises buried in that single dataset. The second surprise hit the moment the team mapped out exactly where on Neptune's globe this glowing light was actually located. On Earth, auroras cluster tightly around the north and south poles. The same is true for Jupiter and Saturn, neat, well-defined ovals wrapped around each planet's rotational axis. Neptune's aurora showed up nowhere close to its poles at all. Instead, it appeared at the planet's mid-latitudes, roughly the same relative position on Neptune's globe that South America occupies on Earth's. If you have spent your whole life assuming auroras are strictly a polar phenomenon, this finding should feel genuinely strange, because it overturns that entire assumption for at least one planet in our own solar system. The explanation traces directly back to something Voyager 2 discovered during that same brief 1989 flyby, and which scientists had spent decades trying to fully make sense of. Neptune's magnetic field is not neatly aligned with its rotational axis the way Earth's roughly is. It is tilted a staggering 47 degrees off-center and offset from the planet's core entirely, making it one of the most chaotic, lopsided planetary magnetic fields ever measured anywhere in the solar system. Because auroras form specifically where a planet's magnetic field lines funnel charged particles down into the atmosphere, and because Neptune's field points so dramatically away from where its poles physically sit, its auroras simply do not gather where poles usually are. They gather wherever those twisted, tilted field lines actually happen to converge, which turns out to be nowhere near the planet's geographic top or bottom. Neptune's northern lights, in the truest sense, are not northern at all. Two surprises in, and the story could have ended there, a satisfying, tidy resolution to a 34-year mystery. Instead came the third finding, the one Mellon himself called the most astonishing, and the one that reframes everything else in this story. While analyzing that same spectrum, the team was also able to precisely measure the temperature of the very top of Neptune's atmosphere, its ionosphere, for the first time since Voyager 2's flyby more than 3 decades earlier. What they found stopped them cold. Neptune's upper atmosphere had cooled by several hundred degrees since 1989. The 2023 measurement came in at just over half of what Voyager 2 had recorded in 1989. Not a subtle drift within the margin of error. A dramatic, unmistakable planet-wide temperature collapse, unfolding over roughly 3 decades, that nobody had any way of tracking as it happened, because nobody had the instruments capable of checking. And that third discovery, it turns out, quietly rewrites the explanation for everything that came before it. Auroral brightness depends heavily on the temperature and density of the gas being excited by incoming particles. Every prediction scientists had ever made about how visible Neptune's auroras should be from Earth had been built using the temperature of Voyager 2, recorded back in 1989. Nobody accounted for the possibility that Neptune's upper atmosphere might dramatically cool in the decades that followed, because there was no way to check, no spacecraft, no sufficiently sensitive instrument, until Webb finally arrived. A colder atmosphere produces a fainter aurora, faint enough, it now appears, to have simply sat below the detection threshold of every telescope and every observing campaign for over 3 decades. Neptune's auroras were never truly hidden by distance or bad luck or insufficient searching alone. They were hidden because the entire planet had been quietly transforming since the last time anyone got a close look, and not one person on Earth knew it was happening. This is the detail that deserves the most attention, honestly, more than the auroras themselves, because it reframes the entire discovery. This is not simply a story about a better telescope finally spotting something that had always been sitting there in plain sight. It is a story about an entire planet's upper atmosphere undergoing a dramatic, unmonitored transformation across 3.5 decades, while every assumption scientists carried into that search was quietly built on outdated data. Neptune sits more than 30 times farther from the Sun than Earth does, and conventional wisdom long assumed a planet that distant, that isolated, should be relatively stable and slow to change. A hundreds of degrees swing in its upper atmosphere within a single human lifetime suggests something far more dynamic is happening out there than anyone had previously assumed, and raises an uncomfortable question about how many other assumptions built on Voyager's single 1989 snapshot might also be quietly out of date. Heidi Hammel, a Webb interdisciplinary scientist who has studied Neptune for decades and helped lead the observing program behind this discovery, put the 34-year wait in context. H3+, she explained, had already been a clear signifier of auroral activity on Jupiter, Saturn, and Uranus, and researcher S had expected, using the best ground-based facilities available, to eventually find the same signal on Neptune. It simply never came, year after year, until Webb finally made the confirmation possible. Lee Fletcher of the University of Leicester, a co-author on the study, connected the finding to what comes next, noting that as scientists dream of future dedicated missions to Uranus and Neptune, this discovery has shown exactly how essential infrared instrumentation will be, calling Webb's observation the moment that finally opened the window onto the last previously hidden ionosphere among the solar system's giant planets. There is a genuine irony sitting at the center of all 3 of these findings stacked together. Neptune's auroras were not glowing in some remote, unexplored corner of the solar system nobody thought to check. They were glowing on one of the most photographed, most studied planets in our night sky, a world humans have known about since 1846. A planet Voyager 2 flew directly past and photographed in exquisite detail, and yet an entire visible phenomenon sat completely undetected for over 3 decades, hidden by a lopsided magnetic field pointing scientists towards the wrong location, and by a dramatic atmospheric cooling nobody had any way of tracking, layered one on top of the other. Sometimes the biggest gaps in our knowledge are not hiding in the places we have never looked. They are hiding in the places we have studied for centuries, simply because our assumptions never caught up to how much the target itself had quietly changed. Scientists are not treating this as a closed case. Having finally confirmed the auroras exist, pinpointed exactly where they appear, and identified why they went undetected for so long, the team now wants to do something never before attempted for this planet, watch it change over time. Neptune, like every planet in our solar system, responds to the Sun's roughly 11-year solar cycle, the periodic rise and fall in solar activity driven by shifts in the Sun's own magnetic field. Astronomers now hope to use Webb to study Neptune's auroras and upper atmosphere across a full solar cycle, tracking how that mid-latitude glow brightens, dims, and shifts across more than a decade of continuous observation, something that was simply impossible before anyone could reliably see the aurora at all. If it works, it could finally explain not just where Neptune's magnetic field points, but why it is tilted so extremely in the first place. A question that has sat open since Voyager 2 first measured that bizarre 47-degree offset back in 1989. Neptune remains, even now, the most distant and least explored planet in our solar system, visited exactly once, briefly, by a spacecraft that will never return. Nearly everything learned about it since that flyby has come not from getting physically closer, but from building better and better ways of looking from far away. This discovery stands as the clearest proof yet of what the patient, distant observation can still uncover, layer after layer through. Separate secrets stacked inside a single spectrum, one glowing signature nobody had confirmed in 34 years, one location nobody expected, and one temperature collapse nobody was watching happen, all sitting quietly in the data of a planet we thought we already understood. If this story surprised you even a little, hit subscribe, because Neptune is still changing out there right now, and we are only just beginning to watch it happen.